So now we're going to take what we learned from Schrodinger's wave equation, and that is the wave function is dependent upon n, l, m sub l, and m sub s. And basically, what we already know is described by the Pauli exclusion principle, and that is that no two electrons in an atom can have the same four quantum numbers. So that means that every atom, or every electron in an atom, has a unique quantum address that are defined by n, l, m sub l, and m sub f values. So what does this mean? It means that only two electrons can occupy any orbital. Hence, the maximum number of electrons in any orbital is 2. And for each n energy level, we can calculate the total or the maximum number of allowed electrons by using this equation, which is, whoops, get my pen working here, 2 times n squared. N being the principal energy level. So if we are in n equals 1, the first energy level, then 2 times 1 squared equals 2. And that is the maximum number of electrons allowed in an s orbital. Okay? All right, so electrons with the same value of n are in the same principal energy level. If the electrons have the same value of n and l, they are in the same subshell. And electrons with the same values of n, l, and m sub l are in the same orbital. So the only thing that defines their difference is going to be m sub s. How many electrons can an orbital hold? 2. One has a positive spin, one has a negative spin. So the quantum numbers for an electron in the same orbital will have the same n, l, m sub l, but their m sub s will vary. It's either plus 1/2 or minus 1/2. Sorry, I've got a scratchy throat this morning. So I want to summarize the quantum numbers again before we move on and write a set of quantum numbers. And of course we have the n, we have l, we have m sub l, excuse me, and of course we'll have m sub s. What I haven't mentioned before is that for those of you who have been exposed to writing electron configurations, you are accustomed to describing subshells by using letters, and those letters are S, P, D, and F. But they correspond to L, and the values of L are 0, 1, 2, and 3. So if L equals 0, we're in an S subshell, L equals 1, we're in a P, and so forth. So n, values of n are 1, 2, 3, and so on. The values of L range from 0 to n minus 1. We can determine the number of orbitals and their orientations by multiplying 2 times L plus 1. But also, M sub L values range from minus L to plus L. So if we want to know the number of orbitals, we can use this equation, but the range of values for M sub L is given by this, or that's the range, okay? So if we have a principal energy level of 1, we can have one subshell. So remember, this is the subshell. This is the principal shell, or principal quantum number. And this is the orbital's orientation in space. That's M sub L. And so we're just looking at Schrodinger's quantum numbers right now. If L is 1, we can have one subshell. That's the S subshell. Whoops. So the value, or the integer, for L is 0. It corresponds to an S. Okay. M sub L minus L to plus L for an S subshell is also 0. And you know what? I think I'll put the number of orbitals over here. We have one orbital. 2 times L, which is 0 plus 1. And the letter designation for that orbital is S. If we're in an n equals, I don't know why this pen is 2, we can have two subshells. 0 to n minus 1. N is 2, so 2 minus 1 is 1, so we can have 0 and 1. If L is 0, M sub L is 0. And we have one orbital, and that's the S orbital. If L is 1, we have, well, we're in a P subshell, and we have 3 orbitals. In the P subshell, and the quantum numbers that are identify those 3 orbitals range from minus L, or minus 1, to plus 1. And we are, as I said, in a P subshell. I'm going to go to n equals 3 and 4 on the next page. So if n equals 3, we can have 3 subshells. So L can have values of 0, 1, and 2. So 0 to n minus 1. These headings up here. So if L is 0, M sub L is 0. We have one orbital, and that's the S subshell, or S orbital. If L equals 1, we're in a P subshell. We have 3 orbitals. Letter designation is P. If L equals 2, our M sub L range is from -2 to +2. And we have 5 orbitals. 2 times 2 plus 1. Okay. And the M sub L are the description of the orientation in space. And if L equals 2, then we are in a D subshell. And for N equals 4, we can have 4 subshells, and so L can equals 0, 1, 2, or 3. Again, if L is 0, M sub L is 0. We have 1 orbital, and that's the S. If L equals 1, we have 3 orbitals, and we're in the P subshell, or the P orbitals. N equals 2 minus 2 plus 2, 5 orbitals, which corresponds to D. And then finally, N equals 3. We have 7 orbitals, and we are in the F subshell. Okay? Now, we're actually going to write a set of quantum numbers. Okay? And so we are being asked to assign a set of 4 quantum numbers. For the electrons in oxygen, which has 8 electrons. Okay? Now, we haven't talked about, or reviewed, I should say, electron configurations. That's coming up in the next video. However, you should have been exposed to them before. I am going to write the electron configuration for oxygen with a total of 8 electrons. We've got 2 in the 1s, 2 in the 2s, and 4 in the 2p. And I'm also going to draw the orbital diagram for oxygen. So this is the 1s, this is the 2s, and this is the 2p. There are 2 electrons in each of the s orbitals, and we have 1, 2, 3, 4 in the p. And we'll discuss how these are filled when we review orbital diagrams. The reason I do this is I'm interested in assigning the correct M sub L for those 2p electrons. And blow this box up, or this subshell. So these are the 3 orbitals in the p subshell. This is -1, 0, and 1. Okay? So the first thing I'm going to do is identify how many electrons are in each orbital, or how many electrons are in each orbital. We have 2, 2 electrons in the 1s, and I'm separating them. We have 2 electrons in the 2s, and then we have 4 in the 2p. Okay? And we need to assign N, L, M sub L, weaks, and M sub S. So 4 quantum numbers for each of these 8 electrons. N's are easy. Our N's are given over here. We've got 2 electrons in the N equals 1. We have 1 in each of the N equals 2s. I'm sorry. I'm doing the N values here. Never mind. I'm not thinking. So this is 2. 2. All of these are 2s. These 6 electrons are in the same principal energy level. Okay. These 2 electrons are in the same principal energy level. And they're also in the s orbital. And when n equals 1, L equals 0. Okay. When L equals 0, M sub L also equals 0. So these 2 electrons have the same N, L, and M sub L. The only thing that distinguishes them from one another is the spin, or the magnetic spin quantum number, which is either plus 1/2 or minus 1/2. So the set of 4 quantum numbers for these 2 electrons are written like this. Well, for all of these, for that matter. So this is how you write a set of quantum numbers. I'm showing you how I like to organize this so I get them right. So let's jump up to the 2s. We're still in an s orbital, so L equals 0, M sub L equals 0, and they're in the same orbital, so their spins are opposite in charge. So now we have 2, 0, 0, plus 1/2, 2, 0, 0, minus 1/2. Now we're in the 2p. When L equals 2, I'm sorry, L equals 1. We're going to P subshell, L equals 1. So all of these are in the P, so their L is 1, okay? So same principal energy level, same subshell. But there are only 2 of them that are in the same orbital, okay? And the way I've labeled these, the 2 that are in the same orbital have an F sub L of minus 1. And then we have 1 in the 0 and 1 in the 1. These 2 will have offset spins. And you'll notice here I placed both of these electrons in the up position. So the rule when filling orbitals with electrons is you put 1 in each orbital with the same spin before you go back and start pairing them. And this is Hund's rule, which I guess is toward the end of this video, but we're already addressing it. So the quantum numbers for the two electrons that are in the same orbital are 2, 1, -1, +1/2, 2, 1, -1, -1/2. And these will have the same spin. I call the up position the positive, down negative. It doesn't matter which one you use, as long as when you start filling the boxes or the orbitals, they are all in the same, all have the same spin. So that is how you write a set of 4 quantum numbers. I had an extra side in case I ran out of room. Okay, for the energy of orbitals in a single electron atom, of which there is only one, that's hydrogen, the energy depends only on the principal quantum number. And that should make sense, because if we have one electron, it has to be in n equals 1. Okay? And again, this is, we can use that equation to calculate n of that principal energy level. And we can use it for the other levels too. But if we have only a 1 electron atom, that principal energy level is the only thing that matters. The energy of orbitals in a multi-electron atom, however, depend on both n and l. Okay, and as you can see here, there's a large jump in energy, or difference in energy, between the 1s and 2s, but there isn't a very big jump between 2s and 2p. And as we go up, those differences in energy, even though we're getting further away from the nucleus, the energy differences between the subshells, and there also becomes an overlap, gets smaller. So normally we would, we'll fill the 1s, the 2s, the 2p, the 3s, the 3p. But you see that we're going to fill the 4s before we fill the 3d, and then the 4p is filled, then we go to the 5s and the 4d. So there's overlap in energy once we hit n equals 4. And we'll talk about that and see that when we practice those or review the electron configurations. And this is just giving you the values here of L. Okay, Hund's rule I mentioned a moment ago. It's the most stable arrangement of electrons in subshells that occurs with the greatest number of parallel spins. Okay, and that's what I meant by so we have one unpaired, so this is carbon, we have 1 electron. When we add the next electron, it goes in the next orbital with the same spin. If we look at nitrogen, we're going to add 1 more, same spin, go over, to oxygen, which we did look at. Now we're starting to pair those electrons. Fluorine, we pair 2 sets, and then finally neon, we fill that p subshell completely. Okay, so that's Hund's rule. So we can classify substances based on their magnetism. And the terms used for their attraction or repulsion to a magnet describe these substances. So if a substance or an element is paramagnetic, it is attracted to a magnet. So this is attraction. And it has unpaired electrons. Okay. If a substance is repelled or repulsion, that substance is diamagnetic, and all the electrons are paired. Okay. So basically what this boils down to is diamagnetic substances do not contain net unpaired spins and are slightly repelled by that magnet. So that means all spins are paired versus the paramagnetic substances that do contain net unpaired spins and are attracted by that magnet. So, as a rule, any atom with an odd number of electrons will always have one or more unpaired electrons. However, atoms with an even number of electrons may or may not contain unpaired spins. So it is very important, if you are asked to classify an element or substance that has an even number of electrons, you draw the orbital diagram. And this last slide in this video just introduces or refreshes, hopefully, our memories on what an electron configuration and an orbital diagram are. In the next video, I'm going to go over the rules for writing electron configurations, and we are going to do some practice problems regarding writing configurations and drawing orbital diagrams. So the electron configuration describes how the electrons are distributed among the orbitals in an atom. So this is the principal quantum number. This is the subshell, which we also know now is the angular momentum represented by a letter in the configuration, rather than an integer in a set of quantum numbers. And the subscript, numerical subscript, is the number of electrons in that orbital or subshell. And the orbital diagram, and this example is just for the one electron atom hydrogen, we draw boxes to indicate the orbitals, and then of course show the electrons occupying those orbitals with arrows.